problem 1, we are given that the joint distribution function of fxy is equals to 1 plus xy divided by a, and the range is the absolute value of x is smaller than 1, and the absolute value of y is smaller than 1. And so this should be this region. And for part 1, in order to make the fxy a valid joint density function, we should do the double integral within the defined region here. So we integral from x from -1 to 1 and y from -1 to 1, and we plug in the density function, integral from do double integration, and this should be equal to 1, and we solve that a is equal to 4. And for the problem 2, in order to show whether x and y are uncorrelated or not, we calculate the correlated coefficient c, and c is equals to the expectation of xy minus the expectation of x times the expectation of y. And so to calculate c, we calculate the expectation of these three things. And for the expectation of xy, we just plug in, it should be the integration of xy times the joint density function of xy, and do this double integral of dx dy is from -1 to 1. And we just plug in the value of a we just get from part 1. And we get that the expectation of xy is equals to 9/1. And for the expectation of x, it should be the double integral of x times the joint density function of xy, and integral over this square region, and it's we plug in the value. It should be x power of 2 times y over dx dy. And after calculation, we get this value is equals to 0. And we calculate the expectation value of y because it is symmetry. X and y are actually symmetry. So we also get the expectation value of y is equals to 0. And we get that c is equals to 1/9 minus 0 times 0 is not equals to 0. So because c is not equal to 0, x and y are not correlated, are not uncorrelated, I'm sorry. And for the problem C, because we have a theory that if x and y are independent, then they are uncorrelated. And applied negative inverse of this theorem, we get that if x and y are not correlated, then they are not independent. They are not independent. And because we have derived from part 2 that x and y are not uncorrelated, so we get directly that x and y are not independent. And this is for the parts 1, 2, and 3. And for the part 4, we are going to find the joint density function of x power of 2 and y the power of 2. And I just rewrite the density function here. And in this case, this problem, we apply the fundamental theorem. We use a variable z equals to gxy is equals to x power of 2, and we define w equals to y the power of 2, and we calculate the Jacobian. J is equals to the derivative of z with respect to x is 2x. Derivative of z respect to y is 0. And similarly, we get derivative of w with respect to x is equals to 0. And with respect to y is equals to 2y. And it is equals to 4xy. And then we calculate the root of this equation set, and we know that there are 4 roots. The 4 roots are x equals to square root of z, y equals to square root of w, x equals to minus square root of z, y equals to square root of w, x equals to square root of z, y equals to minus square root of w, x equals to minus square root of z, y equals to the minus square root of w. There are 4 roots. And so we apply the fundamental theorem. We get that fzw is equals to 1 over the Jacobian. Jacobian is 4xy. And if we plug in the we use zw to express xy, and we take the absolute value. It should be 4 square root of w times square root of z. This is 1 over the absolute value of Jacobian. And times the 4 roots. We just plug in the roots of and take the roots to calculate the probable joint density function value. And since there are 4 roots, so we have 4 terms here. And after calculation, we get that the joint density function of ZW, which is also the joint density function of x power 2 and y the power of 2, is equals to 1 over 4 square root of z square root of w, and w is from 0 to 1 because w is equal to y the power 2 and z is from 0 to 1. And in the fifth part of this problem, we need to prove or disprove whether x power of 2 and y power of 2 are independent or not. So to find whether independent, we just calculate the density function of fx times the density function of fy and compare whether it is equals to the joint function of fxy. And here we need to calculate the joint density function of this here, this x should be x should be z, right? Y should be w. Here should be zw. And as we already calculated the joint density function of zw in part 4, so we calculate the joint density function of z. And here I make the previous part smaller so I can write in one page. And to calculate the density function of z, we just do the integration of w, and w is from 0 to 1. And we plug in the value. I'm sorry. Integral of dw, and it is equals to here. And due to the symmetry, we get the density function of w is the integral of the joint density function of zw with respect to z, and we get it is equals to 1 over 2 times the square root of w. And because we have seen that the density function of z times the density function of w equals to the joint density function of zw, so we can conclude that z and w are independent. And because z is equals to x power of 2 and w is equals to y the power of 2, so x the power of 2 and y up the power of 2 are independent. This is for the problem 1.